So let's consider questions from the theoretical past papers related to the nuclear physics. So, like the last part of this question, the C part, in C part of the question, we have to state two different sources of background radiation. So you can write name of any two background radiations. We have cosmic rays, rocks. So these are the sources of background radiations. Okay. Question number 8. The isotope uranium-235 is represented by this symbol. State what the number 92 and 235 represent in this symbol. So what is the meaning of 92 in this symbol and the meaning of 235 in this symbol? So 92 represents the number of protons, and 235 represents number of nucleons. Nucleons means neutron plus proton, right? So this is the meaning of number 235. Okay, next part is related to the nuclear reactor. So let's find some other question. Okay, if we continue with this third part of the question that we left because of the half-life concept. Now in this question, the isotope of neptunium produced by americium-241 is also radioactive. So if we have isotope of this element that is produced by americium-241, so it is also radioactive. Now the decay of this isotope of neptunium produces an isotope of protactinium which decays by beta emission. So we have isotope of neptunium and that produces protactinium and which decays by beta emission. So we have neptunium and this neptunium performs beta decay. And after beta decay, you will get another element called protactinium. So beta particles are more penetrating than alpha particles. The half-life of neptunium is longer than 2 million years. So using this information, explain the advantage of this long half-life for the use and safe disposal of a household smoke alarm. So let's suppose if we are using a small half-life, right? Sorry, a long half-life. Long half-life means that the decay rate of this element is very slow. It takes many years. You can see 2 million years. So it takes 2 million years to decay uh, into the half of its original value. Okay, so this is like a very long time. It is greater than the normal living age of the human being. So what is the advantage of this long half life? Any idea? Any rough idea if we have an element having so much like lengthy half life?
It won't be as dangerous.
Okay, so basically it consists of a long half life. It means it will emit radiation with very slow rate. A small amount of radiations are coming out from the element. So that's why the half life of this element is too long. So this is one advantage. Any other thing in your mind related to the long half life that you want to share? So the first thing is correct, that we have less number of emission of radiation per unit time. And if we talk about another point, because this question is for 2 marks, this will give you only 1 mark. So for the other mark, we can say that if you are using this element in your smoke alarm system, so you can use this smoke alarm system for long time and it is also not harmful to the humans, right? So these smoke alarms are not harmful or hazardous to human. So this is another advantage of using long half-life, correct? Okay, next question number 9. Table 9.1 shows some properties and values for alpha particles, beta particles, and gamma radiation. Now complete table 9.1. State how beta decay changes the nucleus of an atom. So let's suppose if you consider any element, and first of all we have to complete this table 9.1. Then we have to answer that how beta decay changes the nucleus of an atom. So let's complete the table first. We have a number of protons given for alpha, and how many number of neutrons are there for alpha radiation? There are total 2 neutrons. So 2 plus 2 gives you 4. So alpha is like a helium element. So 2 proton and 4 number of nucleons, right? Next, if we talk about beta, so how many protons are there in in beta? You know how to write the symbol for beta. So with the help of that symbol, you can identify how many protons are there. So beta is simply a fast moving electrons. It means we have zero number of protons in beta. because beta is like itself a fast moving electron. So how proton number will be present in electron only, right? Now the second thing is about the charge. In alpha, we have +2 charge. For alpha, we know we have +2 charge, and for beta, we have -1 charge. So because of +2, your value is 3.2 10 to the power -19. But in beta, we have only one charge, like one negative charge. So this value 3.2 10 to the power 19, this is the total charge of two protons. So if you divide it by 2, so you will get the charge of one proton, right? And for electron, we know we have to just write minus sign with it, because minus represents electron and plus represents protons, correct? So we have to divide this quantity by 2, so to get the exact number of the one proton or one electron. And for electron, we just need to change the charge from positive to negative. So 3.2 exponent minus 19. 3.2 exponent minus 19 divided by 2. It is minus 1.6 10 to the power minus 19. Correct? Any confusion in this? Okay.
No.
Then if we talk about the number of neutrons in gamma. So what about the number of neutrons in gamma? Again, we have zero number of neutrons because there is no charge on gamma. So it means no positive, no negative, no neutral. So there is no charge on gamma, zero charge. And it can be stopped by thick sheet of lead, right? Okay. Now, the B part of the question, state how beta decay changes the nucleus of an atom. So when beta decays from the nucleus, so we studied and we write the properties of alpha, beta, and gamma. In beta decay, if you compare with equation, this is the equation of beta. So in beta, we have -1. This is one electron. So basically, the change in the nucleus takes place like this, that one nucleus converts into one proton and one electron, right? One neutron converts into one proton and one electron. So this is the change takes place in the nucleus of an atom, that one neutron converts into one proton and one electron, right? Any confusion in this? Now the C part, a radiation detector used in a laboratory detects a background count rate of 30 counts per minute. A radioactive source is placed in front of the radiation detector. The initial reading on the detector is 550 counts per minute. The half-life of the source is 25 minutes. Calculate the expected reading on the detector after 75 minutes. So in your question, half-life is already given. Half-life is 25 minutes. And we also have a background count rate of 30 counts per minute. This is the background radiations. Background radiations. And when you place radioactive source in front of the radiation detector, the initial reading on the detector is 550. So this is the initial value. And this initial value includes the value of the radioactive sample plus the background radiation, correct? So first of all, we have to correct this value for the background radiation. So 550, first of all, we have to find out the correction for background radiation. So for example, if we need to find out the correction for the background radiation, so let's see how it works. The initial value given in the question is 550 counts per minute. Minus the background radiation is 30. It is equals to 520 counts per minute, right? Okay. Next, we got a value without background radiation. So let's start taking the half-life of this value because they are asking about the expected reading on the detector after 75 minutes. And the half-life is 25 minutes. So 25 plus 25 plus 25. It means if we 3 time add 25, so you will get the value of 75 minutes. Okay. So it means we have to perform 3 half-lives. So let's calculate half-life for total 75 minutes. So we have 520 divided by 2, 260, right? Then further split into half, 130. In the first half life, it takes total 25 minutes. This is the first half life. And then in the second half life, it further takes 25 minutes. 25 plus 25 is equals to 50. So you will get next half life after 50 minutes. And the last, it gives you 65. So this is the value of half-life after 75 minutes. And this is the value for the radioactive element, correct? But what do you think when this radioactive element is placed in front of the detector after 75 minutes? So it will show the background radiation or not? If this element is placed in front of the detector even after 75 minutes, so what do you think, that still we have background radiations or not? Still we have background radiations. So what we need to do, we need to again add the background radiation in the final result, because initially the background radiation is given and we subtract from the given value, and when we subtract from the initial reading given for the radioactive element, so you will get the original value for the radioactive sample, which is 520. And we calculate the half-life. First half-life 25 minutes, second half-life 50 minutes, third half-life 75 minutes. And after 75 minutes, the radioactive sample decays to the value of 65. But now again, the background radiation are still present in your surrounding. It means the reading detect by the detector includes the background radiation also. So if we talk about the reading of detector, 65 plus the background radiation is 30, gives you 95, right? Any confusion? So basically, when we are using a detector, so always remember detector always detects the background radiation, because detector is not able to differentiate by itself that either these radiations are coming from background radiation or from the radioactive source. We are humans, so we can identify when we place radioactive elements. So it means radiations are coming out from radioactive element plus the background radiation. But when there is no radioactive element placed in front of the detector, it means we only have background radiation present in the atmosphere, and the detector records the value of the background radiations only, right? Any question? Okay. Question number 9. Figure 9.1 represents all the particles in the neutral atom of a radioactive isotope X1. Determine the number of neutrons in this atom and explain how the answer is obtained. So in this question, how many number of neutrons are present? So we know that for the number of neutrons, we have to first count the number of protons and number of electrons, because number of protons and number of electrons are always equals to each other. So you can see we have 6 electrons present. Okay, so your answer is 7. We have 1 electron, 2 electron, 3, 4, 5. So we have 5 electrons. It means we have 5 protons also. So these light circles are proton 1, 2, 3, 4, 5. So we have 5 protons, and rest of the dark circles represents the neutrons. So those dark circles are equals to number 7. So those are neutrons. Okay. And now we have to write explanation also. Explanation is simple, that number of protons are equals to number of electrons. So that's why in the nucleus we have total 5 protons present in the nucleus. B part, the isotope X1 is a beta emitter that decays to the stable isotope X2. Describe how a nucleus of X2 differs from the nucleus of X1. So isotope X1 is the beta emitter. It emits out beta that decays to the stable isotope X2. Describe how a nucleus of X2 differs from a nucleus of X1. So X1 emits beta and it decays into a stable isotope X2. And now we have to compare the nucleus of X2 from the nucleus of X1. So basically when X1 emits beta, in beta we know we have one electron, one proton and one neutron actually converts into one proton and one electron. So the nucleus of the stable isotope to X2 consists of one more proton just like in this equation we discussed for beta. So you have one more proton and neutron numbers are same. So this is the only difference, that the nucleus of the stable isotope X2 consists of one more proton than X1. And you can also write one neutron splits into proton and electron, and suggest why X2 is a stable whereas X1 is not stable. So any reason in your mind why X2 is more stable than X1? So basically, if we talk about X2, so X2 have uh, less number of neutrons because one neutron converts into one proton and one electron. So X2 contains one less neutron in the nucleus. Correct? Any confusion?
No.
Okay. Okay. So this is the difference in x2 as compared to x1. Clear? Any confusion?
No. Yes.
Okay. And okay. So we have half-life also. The half-life of x1 is approximately 20 milliseconds. Determine, define the term half-life. So the term half-life we already discussed in our notes. It is the time taken by the radioactive elements to decrease its number to the half of its initial value. So we just need to copy paste that definition. And second part, suggest one reason why isotopes with very short half-lives are especially hazardous. So in the previous question, we observe half-life of like so many millions here, and now they are talking about short half-life. So in a short half-life, definitely they emit out radiation quickly. So rate of radiation or rate of emission of radiation is very high. So we are getting so many radiation in short interval of time. So we can say because of large, or we can say high decay rate. Correct? So this is the complete question for 8 marks. Question number 10. The magnitude of the charge on beta particle is 1.6 10 to the power minus 19 coulomb. State the proton number, nucleon number of an alpha particle. So it is very simple. The number of protons present in the alpha particle is equals to 2. Nucleon number means neutron plus proton. So that is equals to 4. Second part, determine the magnitude of the charge of an alpha particle. So what is the magnitude of the charge of an alpha particle? So magnitude of the charge we discussed in the second last question, 1.6 power minus 19 coulombs. We also discussed this value in the electricity section. So in electrostatics, we studied that the charge of one proton and the charge of one electron both are same. Only there is a difference of positive and negative sign. Otherwise, they have same values. Then we have B part. A nucleus of radium-230 consists of 88 protons, 142 neutrons. Radium-230 is radioactive and decays by beta emission to an isotope of actinium. The symbol for radium is Ra and the symbol for actinium is Ac. So write down the nuclide equation for this decay. So let's see the equation. Okay. Now in the B part of the question, we have to write down the equation. So the starting element is radium 230 consists of 88 protons, 142 neutrons. So radium 230. So in start we have radium 88 protons and 230 nucleons, and it decays by a beta emission. So we have beta -1, 0 to an isotope of actinium, and the symbol of actinium is AC, AC 89, 230. Correct? And the C part, the half-life of the radium 230 is 90 minutes. A sample contains this much grams of radium 230. Calculate the mass of radium in the sample after 279 minutes. So now in this question we have half-life given of 93 minutes, and a sample contains this much grams of radium 230. So calculate the mass of radium in the sample after 279 minutes. So first of all, let's see. Initially, we started from 9.6, 10 to the power minus 12. This is the initial mass of the radium 230. And now 279 is the total time. Like after 279 minutes, we have to find out how much mass will be left. So if you divide 279 by 93 to find out the number of half-life. So if we want to find out the number of half-lives, like how many half-lives takes place. So 279 divided by 93, 3. It gives you 3 half-life. It means we have to perform 3 half-lives to get the final answer. So let's perform the half-life. So we have a sample divided by 2. It gives you 1 half-life. 9.6 exponent minus 12 divided by 2. It is equals to 4.8. Again, second half-life. So after second half-life, it is equals to 2 2s are 4, 2 4s are 8, 2.4. Then the final half-life gives you the value 1.2 minus 12. So this is the first half-life. This is the second half-life. and this is the third half-life. So you can see after total performing the three half-life, we got the final mass equals to 1.2 10 to the power minus 12 grams. Because we have 93 minutes of half-life, so the first half-life takes place in 93 minutes. Then 93 plus 93 equals to 186. So after second half-life, we got total 186 minutes, and finally 279. And the final answer 1.2 minus 12 grams, right? So this is the final answer of this question, right? Any confusion in this?
No.
Okay. Okay, so the starting part of this question is same about the isotope and number of protons, number of neutrons, right? So that is very easy. So let's solve the graphical representation of this question, because this is the first question in which we are getting graphical representation. A sample of gold 198 is placed near to a radiation detector in a research laboratory. The count rate is recorded at the same time every day for 32 days. And you can see this is the graphical representation we got from the observation after 32 days. Uh, Using figure 9.1, determine the background count rate in the research laboratory. So can you identify the value of the background count rate from this graphical representation? Any idea? So answer is very simple to identify from this graph. Always remember when radioactive elements starts to decay. So definitely because of the decay, the value starts to decrease and it is moving towards zero, right? 100, 50, 25, then 15.5 something. So it is moving towards zero. But you can see in the graphical representation, it becomes constant at the end of the graph. So in the last, like from here, we have a constant value. It means that rather than going towards the zero, it gives you a constant value. So this constant value is because of background radiations, correct? And this is the value uh, 20, 30, 40, 50, 60, 70, 80, 90, 100, yes. So 20 is the background radiation, correct? Because this value is constantly given in the graphical representation, so it is not decreasing, because background radiations are not like performing radioactive decay, so that's why those value remains constant. So the value is 20 counts per minute, correct? And the third part is using figure 9.1 again, determine the half-life of gold 198. So first of all, we have to subtract the background reading. Background radiation is 20 and the initial value starts from 300 90, right? This value represents 390. So first of all, we have to subtract 390. We have to subtract background radiation from 390. So to get the original value of the gold, which is radioactive, counts per minute. Now let's start finding out the half-life. 370 divided by 2, 180, 5 counts per minute. So if you find out this 185 count rates from the graphical representation, so 150, 60, 70, 80, this is 185. So 185 means this is 2. 2.4, 2.8, 3.2. 3.2 days, correct? Okay, so this is the value without the background radiation. But again, just like in previous questions, we discussed that because of the background radiation, detector always detect those background radiation, right? So it means in your final answer, you have to add the background radiations. So this is not your final answer because this is without the background radiation. So in final value, you have to again add the background radiation, which is 20. That gives you value 205. Because counter always reads the background radiation. 205 counts per minute. Okay. So now we have to identify 205. So this is 200, 205. So this is the value. So it gives you the result 2, 2.4, 2.8. 2.8 days. So this is the correct answer. 2.8 days. Right? This is the final answer. So in this way, you can solve the half-life question related to the background radiation. First of all, you have to subtract to find out the original half-life of the element. Then in your final answer, you need to again add that background radiation because counter always reads all type of radiations, right? So that's 5. Finally, we have to add background radiation. Then we have to find out the result from the graphical representation. And this is the answer. 2.8 days is the half-life of the gold. Okay. So these are some questions related to the nuclear physics from the theoretical past papers, right?